Okay guys, so here is another example of a combined techniques question, what I would call the big table method. If you haven't seen my first video on this, go and watch that now because I give a bit more of an in-depth explanation of how this all works. This is designed as a practice question for you guys to try and apply what you've learned in that first video. So here are the graphs. Hopefully you can identify which one's which now. We've got the infrared, mass spec, carbon and hydrogen. We've also got the empirical formula, which is C3H8O. Stop the video now, have a go at using those graphs and this method. And if you remember, there's an extra bit else on the method which I can't fit on now because I've only got a certain size board. Have a go at using that method, come up with your answer, and then when you're ready, press play and I'll go through the answer with you. Welcome back. So, how would we do this? First of all, we'll look at the empirical formula, look at the elements involved, get that in our head, and go straight on to the mass spec. So, M plus is 60, therefore the MR is 60. Now, like I said in my last video, you probably won't be given all of this to do. They'll just select certain bits for you to do and they'll give you the rest of the information. Or maybe they won't even give you it at all and it's just a harder question. So although you probably won't have to do all of this in one question, I'm going to assume this is like a monstrous question with it all in. So there'll be a lot of marks by the end of this. This would get us 1 mark. We then need to figure out our ratio of molecular to empirical formula, which is 60 over, add all that up, comes to 60, which is 1. I can therefore say my molecular formula equals C3H8O. That's another mark, probably. We can then look at infrared. Well, this broad peak at, what's that, 3,200, something like that? That's going to be my O to H. You might say, is it an O to H in a carboxylic acid or an alcohol? Well, I would look at the wave number to tell that. Absolutely not. They're so close. If you look at the wave numbers, they overlap. You can't tell whether it's an alcohol or a carboxylic acid OH by looking at the wave number. You might say, well, one of them's broad and the other is very broad, so maybe I can look at that difference. What's the difference between broad and very broad? I certainly don't know. Do you know? So that's not going to help you either. The way we check whether this is an OH in an alcohol or a carboxylic acid is by realizing in an alcohol we have a C2O and an O to H. In a carboxylic acid we have a C2O, an O to H and a C double O. So really weirdly, the way you check which one this bond is not by looking at this peak, you look for the C double O peak. If there is one there, it's about 1,700. If there is, it's a carboxylic acid. If there isn't, it's an alcohol. Do we have a peak about 1,700? Do we, knackers? No. So it cannot be a carboxylic acid, it's got to be an alcohol. Also as well, again it's in the fingerprint, so often hard to spot, but I think it's quite useful. We have got a C single O, I've said that about 1,300. And again, you can write down the actual ranges from your data sheet if you don't want to have to try and figure out what it is on the graph. Therefore, it must be an alcohol. 1 mark, 1 mark. So already we could have got up to 4 marks for this. Then with our carbon NMR, we've only got 2 peaks, so we've got one at 80 and one at, what's that, about 35. So again, using our data sheet and all the previous information, the one at 80 is going to have to be a C single O, can't be a C to N because we don't have any N's. That's a C single O. And the one at 35 is going to be a C to C. Okay, probably a mark for that one as well. And again, you wouldn't get all of this in one question, but you could get most of it. Now we come to the NMR table, a lot of marks here. Write down what we know, start from the left. So we've got peaks A, B and C. A, B and C. Chemical shifts are 5.5, what's that, 3.5 and 1.4. Splitting is a singlet. a multiplet. And again, if you've not learned this table with all this, what they look like and how you get them, learn that table. And a doublet. And our relative area, I've just written it above the top. Sometimes it'll be in a table, but it's a 1 to 1 to 6 ratio there. Okay, environment. Let's get our data sheet out. And again, remember, we're dealing with an alcohol. So, a little tip with alcohols and with carboxylic acids, because we have an OH, you have to have an OH in an alcohol and a carboxylic acid, otherwise how would it be that, right? What splitting do OHs always get, and NHs? Always a singlet. OHs don't cause splitting, and they don't get split. So a nice little cheeky tip, if you're dealing with an alcohol or a carboxylic acid, check your graph. If there's only one singlet, that must be the OH. If there's more than one singlet, okay, you need to figure it out a little bit. But look, I've only got one singlet, so straight away, that must be my OH. If you did have more than one singlet, you could check which was the OH by adding deuterium oxide, D2O, and that would remove the OH and the NH peaks. So run your graph, look at where the singlets are, then add D2O, run it again, whichever singlet disappeared, that's the OH or the NH. So that's how we use deuterium oxides. So I've got that. I've also got one at 3.5. So bearing in mind it's an alcohol, that's going to be the H to C to O environment. And at 1.4, that's the H to C to C. So I've done my first two sets of columns. My next two, splitting, tells us the number of adjacent hydrogens. We're going to use the n+1 rule, but kind of in reverse. So 0 add 1 would give us a singlet. Well, this is just lots, so 4 plus. We don't know how many, just 4 or more. And a doublet, well, 1 add 1 is 2, so that would give us a doublet. Our final column, our conclusion, we need to combine our environment and our number of hydrogens, our relative area. But first we need to check that our total for our relative area equals the number of hydrogens in my molecular formula. This adds up to 8, and I have 8 hydrogens, so my relative areas are my number of hydrogens. It's all good. If all of this added up to 4, and my molecular formula has 8 hydrogens, that would mean I would have to double whatever these numbers are. So I'll just write down the double numbers. But it doesn't, it's a bit of an easy one this, so that's fine, we can just keep it as it is. So our conclusion, I've got an OH and 1 hydrogen, well that's just an OH. A H to C to O and 1 hydrogen, so that's just a H to C to O. And a H to C to C and 6 hydrogens. Well, how do we do that then? What is it, C to CH6? Well, that's ridiculous, you can't have that. So it actually could be a couple of things. Most likely by far, it's going to be 2 identical H3C to Cs. So 2 times H3C to C. Technically, it could be 3 H2C to Cs. 2 times 3 or 3 times 2. But it's very unlikely you're going to have 3 CH2s in the same environment. It could happen, but very unlikely. So I would go with this every time first, and then if it doesn't seem to make sense like this, then just kind of rejiggle it and do 3 CH2s. But always start with that one, it would be a good tip. So I've got my 3 jigsaw pieces. All we need to do now is check the cross-linking to see which jigsaw pieces are next to each other. Just to make it actually, I should have just about enough space here. So let's check for cross-linking. And we just need a little sentence, due to complementing, splitting, and relative areas. And then we can figure out what our cross-linking is. Well, this bottom environment here is next to something which has 1 hydrogen on. The middle one has 1 hydrogen. The middle environment is next to something which has 4 or more hydrogens on. The bottom environment has 4 or more hydrogens on, 6. We got a cross-link. And again, when you're practicing, you can do the cross-link. In the exam, I'd actually just do it in my head to stop it getting messy. So these 2 jigsaw pieces must be next to each other. So I've got a H to C to O, and then this carbon here is that carbon there, so I'm going to add on my 2 identical CH3s. And they will be identical because they're coming off the same carbon, and that always makes them identical. Now I've done that, and I'm going to have to get a bit of space now. Now I've done that, I can add on the rest of my jigsaw pieces to make my final molecule. Oh, incidentally, somewhere in this table is going to be 3 or 4 marks, depending on how big the table is. This is quite a small one, so maybe just 3. 1 mark for the per cross-link. Now I've only got 1 cross-link. You can get more than 1. Sometimes there's 2 or 3 cross-links, sometimes there's none. So very finally we need to add on the OH, which hopefully is quite simple for you, to get our final molecule. So proton 2-ol. Let's double check, does the splitting work? Well, OHs are always singlets. Yeah, it's a singlet. This hydrogen has 6 adjacent, so it would be a multiplet. Yep. This hydrogen, now when you've got identical environments, just pick any one and see what splitting that gets. So I can even pick that one. Let's pick that one. It's got 1 adjacent, so it'd be a doublet. Yeah, it's a doublet. So just to finish off, one last safety check. We need to do our fragments. And so my fragments are at 15 and 45. Can we snap off chunks to get these masses? Hopefully you've figured out by now, 15 is always a CH3. Well, CH3 plus. And then 45, we're going to snap off one of the CH3s to leave us with CH, CH3, OH plus. Don't forget the plus. 1 mark for the fragments. This is quite a simple molecule, so probably just 1 for the final answer. The more complicated it gets, obviously the more marks you get for that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 marks. Again, probably wouldn't be an 11 mark question, but certainly could be.